null hypothesis here is that there is no linear relationship. The alternative is that there is some form of a linear relationship. Assuming you have this information, you could come up with your linear model. Y hat is b1x plus b0. Other things that come up along the way while going through all of this information, I have to be concerned about type 1 and type 2 errors. I also need to be concerned about alpha levels. These are my significance levels, and how they relate to C, C being my confidence levels. And I saw that if I was looking at a one-tailed test or a two-tailed test, my pictures would be very different for the two of them. Two-tailed test, if I have C in the center, then alpha would have to be 1 minus C, or vice versa. C would be 1 minus alpha. If I had a two-tailed test, then my alpha would be equal to take the total area in both the tails, 1 minus C, and divide it by 2 to get just one tail order alpha. While it doesn't have all of the assumptions for every single model up there, that is every single model from the class on one board. If you could shrink that and put it onto a 355 note card front and back, you have the note card for your exam. I want to try out one of each different model, whatever we have time to do here, starting very, very quickly with this example in your last quiz. I'm dealing with some sort of ANOVA model here, and I know that this is going to be ANOVA because I'm comparing multiple means. So my null hypothesis would be that the mean for Alejandro A is equal to the mean for Crispy is equal to the mean for Scott. But they all run the mile time in about the same amount of time. The alternative will be that they are not all equal. You'll notice that the alternative really begs the question, well, how are they not equal if I'm rejecting that? I would have to follow this up with doing a bunch of comparisons between these groups. If I'm using ANOVA, then I need to calculate whatever the variation is between my groups and whatever the variation is within my groups. Variation between the groups, the MST, is equal to the sum of all the numbers. First mean minus the overall mean squared, add them up, divided by the total number of groups minus 1. I'm going to set this up to the data that we have so far. If I'm looking at Alejandro, I can count it out and I see that there's 1, 2, 3, 4, 5, 6, 7 runs that Alejandro did. So I have 7 times whatever Alejandro's mile time was. On average, it was 6.46. Minus whatever the overall mile time was. In this case, that was 6.68. Squared plus, and then I'll do the same thing for Chris, where I have 7 times whatever her mile time was minus the overall mile time squared plus, same thing there for Scott, 7 times whatever his was minus overall squared. All over. I'm comparing 3 people. 3 minus 1 tells me I have 2 degrees of freedom between my groups. Assuming I do this, I get for the variation between my groups for my MST is 0.251. The variation within my groups is the MST. That's the sum of all of my degrees of freedom times each of my variances over the total number of elements minus the number of groups. In this case, if I start with Alejandro, there are 6 degrees of freedom for Alejandro. His standard deviation was 0.36. I take that information and square it, and I keep going out throughout the entire list. This is divided by the total number of runs, and I have 7 runs for 3 people, so I have 21 runs, minus the number of groups, 3, gives me 18 degrees of freedom. This gives me approximately 0.10-ish for my mean squares of the error. I'm skipping the part where you type all this information into your calculator, but you're typing a whole bunch of things into your calculator in order to find what each of the means are for each group and what each of the standard deviations are. I expect you to be able to do that. To come up with all of these x bars and s's, I recommend using 1-bar stacks to find all of this information. I have variation between, I have variation within. Using this information, I can move on to calculating my p-value. I know my F ratio is going to be the mean squares of the treatment. That's that 0.25 over the mean squares of the error. That's my 0.10, which gives me an F ratio of approximately 2.51. I like to think of the F ratio like a percentage, so this means I'm taking up 251% of the variation I was allowed to take up, which is a lot. As a result, I should see a small p-value. Now, I don't know if the small p-value means 13% or 2%. I still need to actually find the number, but I would be surprised if this was something like 70%. It should still be relatively small. In order to figure out exactly what that value should be, I do p-value is equal to my F CDF, I'm using F scores, whatever my F ratio was, 2.51, comma, infinity, comma, the degrees of freedom for the top, or the denominator of 2, and the degrees of freedom for the bottom, or the denominator there of 18. If I type this into my calculator, I will end up getting a p-value of approximately 0.11, which is small, but it's still large enough that I'm going to end up rejecting or failing to reject.
Failed.
I'm still going to fail to reject the null hypothesis, because if I'm doing step 4, the conclusion, I will note here that my p-value is bigger than an alpha level of 0.05, in which case I fail to reject the null hypothesis.